Hello everyone, welcome to this video. In this video we shall see question from June 2013 consisting of 4.75 marks. The question is, for a homogeneous Fredholm integral equation, this is the given homogeneous equation, the eigenvalue lambda and the corresponding eigenfunction y of x involving arbitrary constants a and b are which of these four, right? So they are asking calculate the eigenvalues and the corresponding eigenfunctions for the given integral equation. So let us get started. So now observe that the kernel here is separable because you can expand this sine x plus zeta as sine x cos zeta plus cos x sine zeta, right? And so therefore this kernel is of something like this, summation aix and bi zeta, where what is a1x, that is sine x, a2x is cos x, b1 zeta is cos zeta, and b2 zeta is sine zeta, right? So now if we have a kernel like this, which is known as separable kernel, right? In that case, the system is reduced to a linear system. This I minus lambda a into c is equal to f, and f in this case is 0, so this system is eventually 0, right? And I is the identity operator, lambda is the eigenvalue which we need to determine, and a is some matrix whose entries are calculated using this expression. So aik is basically integration from 0 to pi bi zeta ak zeta d zeta, and here fi's are 0, and the determinant and this matrix C, it contains some constants which we need to determine, and this determinant I minus lambda a is d lambda, where this is some polynomial in lambda. Now depending on the value of this d lambda, we have unique or infinitely many solutions. If this is non-zero, then we have unique solution, and because this is the system is homogeneous, therefore the only solution, that is the trivial solution, yx is equal to 0. For non-trivial solution or the non-zero solution, d lambda has to be 0. So when this polynomial d lambda is 0, we'll have certain lambdas. Those lambdas are known as eigenvalues, and the solutions corresponding to those lambdas, they are known as the eigenfunctions. This was the theory. So let us calculate this d lambda, and let us equate this equal to 0 to calculate what are the corresponding eigenvalues and then the corresponding eigenfunctions, right? So d lambda in our case would be I minus lambda into a, I minus lambda a11, a12, a21, 22, where these are calculated using this expression aik. So a11 would be integration from 0 to pi, b1 zeta, a1 zeta, d zeta, where these are the values, right? So you can perform the integration. So a11 comes out to be 0, a12 comes out to be pi by 2, a12 is basically integration from 0 to pi, b1 zeta, a2 zeta, d zeta. So it would be cos square zeta because b1 is cos and a2 is again cos, and we'll use the same variable zeta and we'll take the integration with respect to zeta. So now we can convert this into double angles like this, and we can perform integration and put the limits. So we have pi by 2. Similarly, a21 is also pi by 2 and a22 is equal to 0, I guess. It is equal to 0, yes. So when you substitute all these values back into this determinant d lambda, let us see what do we have. So we obtain d lambda is equal to the determinant of 1 minus lambda into 0 minus lambda into pi by 2 minus lambda into pi by 2, 1 minus lambda into 0. So if you take the determinant, it is equal to 0, and we need that values of lambda for which d lambda is equal to 0. So we substitute this d lambda equal to 0 from here, we get this. So that means these are the eigenvalues. Plus minus 2 upon pi, These are the two eigenvalues of the corresponding integral equation as well as the linear system that we have obtained. So to calculate the eigenfunctions, let us use these values one by one. When lambda is equal to 2 upon pi, then this system, here in place of lambda we'll substitute 2 upon pi. So it would be 1 minus 0, that would be 1, and it would be, when you substitute 2 upon pi, all thing cancels, it would be minus 1, here also minus 1, here also 1. C1, C2, these are the two unknown constants which we have to determine. And once we determine those, the solution would then become something like this. Yx is equal to lambda into summation aix into ci. So c's are 2 here. So let us calculate them. So the system becomes this. So it gives us two equations, C1 minus C2 is equal to 0, or it gives minus C1 plus C2 is equal to 0. When you solve any one of these, you will get the same thing. So here C1 becomes equal to C2, right? So we can replace one constant. So yx eventually becomes lambda into C1 times a1x. a1x was sin x, and C2 into cos a2x. a2x was cos x. And because C1 and C2 are equal, we can replace the C2 by C1. So ultimately it would be C1 times lambda, and lambda here is 2 upon pi, into sin x plus cos x. So in the question they are saying if lambda is equal to 2 by pi, that is the eigenvalue, then the eigenfunction would be some constant. This is some constant. Let us call it as a into sin x plus cos x. So let us look at our option. 2 upon pi and sin x plus cos x. 2 upon pi sin x plus cos x into something. So this is the correct option, right? Let us look at the second eigenvalue. Let us apply the same procedure to calculate the eigenfunctions. So when lambda is equal to minus 2 upon pi, in that case the system becomes 1, 1, 1 and 1. So we'll substitute lambda is equal to minus 2 upon pi into this system over here. So it would give us 1, and here it would be 1, 1 and 1 again. So 1, 1, 1, 1 into C1, C2 is equal to 0, 0. From here you see C2 is equal to minus C1. So when this our yx was lambda into C1 sin x plus C2 cos x, so we could write this as minus 2 upon pi C1. We can replace this C2 by minus C1 and we'll obtain this, right? So now it would be something, some constant, this is some constant, arbitrary constant, into sin x minus cos x. So the eigenvalue, eigenfunction corresponding to the eigenvalue minus 2 upon pi, it would be equal to b into some constant, let me call it as b into sin x minus cos x. So let us look at our options. So option for lambda is equal to minus 2 upon pi, yx is equal to this. So option C is also the correct option. So the only correct options are C and D. That is it for this video. Thank you for watching.